You want to find network errors fast and need a reliable tool. Now what? You are not alone. Try Fiddler Everywhere free for 30 days and let this all-in-one web debugging solution deliver the successful outcomes you expect. Learn more at Telerik.com/Fiddler.
Hello and welcome to the InfoQ podcast. I'm Charles Humble, one of the co-hosts of the show and editor-in-chief at cloud-native consultancy firm Container Solutions. My guest this week is James Clark. James has been contributing to the open source community for nearly 20 years and is probably best known as a pioneer of SGML and XML. More recently, he's been working for WSO2, which is an open source technology provider founded in 2005, where he is the lead designer for the Ballerina language. Ballerina is an open source programming language for the cloud that makes it easier to use, combine, and create network services. It is, I think, a really interesting language that joins others like Go and Rust and Dart as being languages that have been developed for this cloud-native era. And so it's Ballerina that will be the focus for this podcast. James, welcome to the InfoQ podcast.
Hello, thank you for having me. I think it's actually nearly 30 years I've been doing this sort of thing, actually. I'm getting on a bit now.
Is it 30?
Yeah, I think it's nearly 30 now.
Nearly 30 years. Excellent. Well, there we are. So I said in my introduction that Ballerina has been conceived during this new sort of cloud-native era. So how has the shift to cloud changed programming in your view?
I think it changes in a fairly big way. What are the main tasks that a program do? I started programming in the pre-cloud era. You think about how a program gets things done in that era. You were having Perl, and it was, you read files, you write files, and you have APIs, but the APIs are calls to libraries. They're calls to maybe shared libraries or C libraries. They're all on the same machine. So APIs are library APIs, and you get stuff done by writing files, basically. Whereas in the cloud era, you get stuff done by consuming and providing network services. And the APIs that matter are primarily network APIs. So they're sending network messages, typically HTTP, typically JSON. And so what an API is and what the main business of a program is very different. I guess another aspect is concurrency in the traditional C world, if you like. Most application programs don't really need to worry about it. The operating system does, but the application program can just sort of forget about it. Whereas in the cloud, it's pretty pervasive. You've really got to think about it. You can't completely hide concurrency from the application programmer.
And then given that context, what is the specific goal or goals you have for Ballerina? What is it that you're trying to accomplish with the language?
This isn't an academic exercise, so it's very much designed to be a pragmatic language. And it's not designed, we don't want it to be a niche language. We have ambitious goals. We want it to be something that is capable of being a mainstream language. So I guess the initial target is we want it to be a good way to do enterprise integration. I mean, you can start off as a narrow objective, which is we want it to be a good way to do enterprise integration. Good compared to the traditional way, which is an ESB plus some Java. So basically, what do we say? The basic concept is, okay, instead of having a DSL, typically a DSL with XML syntax that has networky stuff that's all about providing endpoints and messages and routing, instead of having that plus Java, let's just have one unified language that you can do it all in. You don't have to have this two language, you don't have to have this split, and you can just do it all in one unified way. And in a way that sort of works, is a good fit for the needs of the cloud.
When I first started looking at the language, one of the things I was struck by was that everything is very explicit. So, for example, there are no implicit conversions between integers and floating point values. An integer overflow causes a runtime exception, and so on. It feels very much like a language that's been designed to favour ease of maintainability over speed of kind of initial implementation, initial typing. Would you agree with that? Is that a fair assessment?
Absolutely. It's a kind of, if I say enterprising mindset, not everybody would understand that in a positive way. Programs are read, real programs, the businesses, rely on serious programs. They have a long lifespan. You've got that crufty COBOL code that's 20 or 30 years old. They're read for years and decades, but being able to read it and understand it is far more important than being able to save a few keystrokes when you're typing it out. So it's definitely a fundamental design goal of Ballerina to favor maintainability, favor explicitness, avoid surprises. And also to leverage familiarity and leverage what people know. The percentage of working programmers who know one of JavaScript, C, C Sharp, Java, C++ is pretty high. And so we want to leverage that so that if you know one of these languages and you look at a chunk of Ballerina code, you should have a pretty good idea what's going on. I may not know every little detail of the semantics of the language, but you can look at it, and even knowing zero Ballerina, you should have a reasonable sense of what's going on. It should not be mysterious.
Right, and that shows up, for example, in the way you do error handling. You don't use the exception method, which is common in languages like Java.
I think there's a significant trend in modern programming languages away from exceptions towards more explicit error handling, where you return error values. So you see that in Go and in Rust, explicit error handling is explicit. You do have the exceptional flow, which are panics, but those are for the really, truly exceptional case. But a regular error handling, and it's a normal part of network programming to have errors, that is dealt with explicitly. You see the control flow explicitly in the program, just like regular control flow. And that, again, is a thing that's a little bit more inconvenient to write. But the poor old maintenance programmer who's coming to look at it can see what are the possible control flows and is going to have a much easier time not screwing up when they try and fix bugs.
Right, yes. I found this really interesting because most of my professional programming was done in Java. And obviously Java has its concepts of checked exceptions, which I think were trying to solve the same problem. But because they allow you to throw a runtime exception, most people do that. So the checked exceptions didn't really work. But I think it's trying to do the same sort of job.
Yes, and the checked exceptions are not quite the same. It shows you which are the possible exceptions. But it's still, you don't know when you call a function, when you see a function call there, you don't see in the call that there is the possibility of it throwing exceptions. You see that there is a possibility of checked exceptions, but it's not explicit in the syntax. So every time you see a function call, you got to go, oh, what are the possible exceptions that can throw? And how is this going to affect the flow of control in the function? And that just makes it harder to figure out what's going on.
Now, you've said that Ballerina isn't a research language. It's intended to be used in industry for real-world applications. And given that, you haven't invented any particularly new ideas from a language point of view. So what is it that makes it distinct?
I mean, there are several different dimensions, but we're starting off from the proposition that what we want to do is make the things that a program has to do today easy. So consume and provide network services, work with data. We want to make those easy. That's one dimension. Another dimension is that we're trying to provide an alternative to a combination of a DSL and Java. And one of the things you can do with the DSL is you can have a graphical view. And the graphical view that you get from the DSL isn't just the syntax. It's not just a syntactic view. It is actually showing you meaningful things about the flow of messages that is possible within your application. And so one of the goals is that you should be able to take a Ballerina program and from that have a graphical view that is not just syntactic. It's not just giving you the classes or the functions. It is actually giving you real insight into how your application is interacting with the network. And it does that by leveraging sequence diagrams. And I think part of WSO2's experience doing enterprise integration for 15 years is that when you talk to customers and they want to explain, how is this application supposed to be working, what they do is they sit down, they write a little sequence diagram, draw a little sequence track, and that gets everybody on the same page. So one of the key features in Ballerina is that you can click on it and you can look at every function as a sequence diagram and you can see the flow of messages in that function. And that is something that's deep, that sort of deeply affects the syntax and it deeply affects the concurrency model. And that's something you couldn't sort of graft on to any other program. So when you get this, it's a two-way model. So you can edit the sequence diagram or you can edit the code, and they're two views of the same thing. You can almost think of it as an alternative syntax for the higher level layers of the language.
Right, yes, and that I think is really interesting and is something that I think is kind of unique. So the graphical representation is a graphical representation of the actual Ballerina syntax tree, meaning that there's no abstraction, there's no translation between the visualization and the code that runs on the platform. If you edit the diagram, you're editing the code and vice versa. So you can genuinely round trip between low code and normal code, as it were.
Exactly. There's no possibility of them getting out of sync as we are now.
Right, yes.
Just for listeners, we're on a different continent, so there's a little bit of a lag. But there's no possibility with these two views of their getting out of sync. And that comes from having thought about this. You couldn't do this just by drawing a pretty layer on top of another language. It's designed in, and it's designed into the concurrency model. The way we do concurrency is it's somewhat limited, and we know we need fancier stuff for the cases it doesn't handle. For the cases it does handle, it provides a more controlled environment. You can really see what's going on, and it's a much easier way to do things. So that's possibly a unique thing. But I think there's deeper stuff too, which goes back to the point about APIs. What is an API in a cloud era language? A cloud era language, it's a network API. So how does a network API differ from a traditional object-oriented API? Well, I think one of the big differences is that you want to do more in each network round trip. Round trips are expensive. So you have typically the parameters to your network APIs are often complex structures. So you're sending data, and whereas your object-oriented API might be set this, set that, and it's a Boolean or int or something, you don't do your network APIs like that. Instead, you want to send in each of your API calls, it's a complex structure, typically JSON, which has a deep nested, typically a tree structure. That's one thing. Another thing is that the different parts of your service are going to be in different languages. One of the beautiful things about microservices is you're not constrained to use one language for everything. You don't have to have a common API or anything. Each bit of your system can be written in whatever language is best suited for that bit. But that means that your messages, your data, the parameters, if you like, to your API, you want those to be data. You want them to be pure data. You don't want them to be objects. You want to send around chunks of JSON that can be interpreted by whatever language each microservice is using. So that means you want a lot of what you want to do in an integration language is deal with this data. It's not objects, it's just data. And you want to take the message you got from one and you want to transform it a bit and you want to send it off to somewhere else. Or you want to combine two of them together into another message and send it off to several different people. But instead, it's not the object-oriented. The object-oriented way is about combining code and data into objects and keeping the data hidden within the object. Opposite of what you want to do when you're dealing with network APIs, you want to expose the data. Well, it may be hidden within your service, but you're exposing the data in the messages that you're sending. It's very much exposed.
Right, yes. I mean, you have this concept of plain data in Ballerina. I was trying to think, I'm not quite sure where that term originates, but could you maybe try and give us a bit of a definition of what plain data actually is in Ballerina?
It's a term that actually comes from, I think it's a C++ term, POD, plain old data. It's just data that doesn't have any methods attached to it. It doesn't make any assumptions as how it's going to be processed. It's programming language independent, and it's therefore inherently mobile. You can serialize it, you can copy it. It's just data. If you're going to try sending functions around, that's not so easy.
And then once you've got your plain data, you can presumably do things like deep copy, deep equality, serialization, deserialization, and so forth, right?
All happens for free. And also, you can serialize it as JSON. You don't need to pre-agree. I mean, if you try to start serializing objects, then you need to agree with the recipient about what are the objects you're going to send. You have to agree on what you're going to call them, all that sort of stuff. But plain data is just much more flexible and has much less coupling and allows your services to be much more loosely coupled. It doesn't create coupling between your services.
And I think that's kind of reflected in your type system as well. So it's a statically typed language, but you've got kind of looser coupling than some other statically typed languages, including things like Java that people are probably familiar with. You have built-in support for JSON and XML, but as I say, the type system it's primarily structural as distinct from nominal, right?
Yes, it's a structural type system. It works in some ways a little bit more like a schema language. You can almost think of the type system. It's really doing double duty, the type system. We're both using it to constrain how, or to check how the operations have been done within the program, but we're also using it to describe the network interfaces to the program. So you can take, when you write Ballerina types, those can also be used to generate schemas for the network interface. So you can generate a GraphQL schema or an Open API from the types. You write the types once, and those types are used both to generate that schema and also to manipulate in just like a regular type system within the program. I think one of the things that makes life very difficult for a modern programmer is they have to continually switch between different worlds. They've got to be a bit of HTML, a bit of SQL. They've got all these different things and they have to manually switch gears between, okay, this is how it works in GraphQL, this is how it works in SQL, this is how it works in my language's type system, and kind of deal with the various impotent matches between themselves. Whereas in Ballerina, you can just express a thing once in the Ballerina type. And because it's almost like a schema, you can map it onto your GraphQL type and you can use it like a regular type system. It also has something called semantic subtyping, which means that you can think of a type as being a set of values. And you can think of the subtype relationship as corresponding to the subset relationship between types, which is something that you see in some schema languages. So you can use Ballerina types to basically describe what's on the wire. So you can have features like, say, that a particular field is optional. That happens all the time in JSON, that you may or may not have this particular field in an object. But most type systems, you don't have that. You have defaults, but that's not the same thing. You're able to describe what's there. Or you can say you can just have this or this. Again, that's an absolutely basic thing when you think of it as a schema, but most languages don't do that. You can't say, well, it's either this or this. You've got to say you've got to have some sort of type hierarchy or something. I mean, TypeScript can do it. And probably TypeScript is the closest of mainstream languages in terms of how the type system works. Because again, what TypeScript is doing is it's describing JavaScript values. And JavaScript values are pretty close to JSON. So you can think of TypeScript as basically describing JSON values. So in a way, it has some similarity to TypeScript. TypeScript is very much tied to JavaScript, which has a kind of anything goes, free and easy, very dynamic view of the world, whereas Ballerina is trying to want to catch your errors. Eventually, we want to be able to compile things into a nice executable. At the moment, the current implementation is based on Java, but that's not part of the language. That's just the current implementation, and we plan to have a native implementation where everything's statically compiled.
I want to return briefly to the concurrency model. We talked about it in the context of the sequence diagrams, the visual aspects, but I'd like to talk a little bit more about the concurrency model in general. So one thing is that you support lightweight threads. You refer to these as strands, and these are analogous, I think, to virtual threads in Java's Project Loom, which we've talked about in a previous episode with Ron Presler on the podcast, so I'll link to that in the show notes. But basically, these strands are runtime managed logical threads of control, right?
Exactly. They're logical threads. I mean, it's very fashionable these days to do everything with asynchronous programming. But I think that makes life awfully hard for the programmer. This whole async thing and promises and all that sort of stuff is just a layer of complexity for the poor application programmer. And I think a thread model where you just present a very simple logical model to the programmer, and it's up to the implementation to turn that into something efficient. I think that's a better model for the programmer. Fundamentally, a threads is a better programming model, I feel.
How do strands enable cooperative multitasking?
Well, so strands, it's as you say, it's a logical thread. So there's these things logically run concurrently. But whether they're actually running on two threads or not depends on whether the compiler can figure out that it's safe to do so. So if we have locking constructs and you haven't used the locking construct, then the compiler will figure out that, okay, we can't run these things in parallel. And so it will switch between them. So you never get two things running on two different threads. And so the various kind of data races can't happen. So in the worst case, it will just run on one thread. And typically when you do some IO, that logical strand will block waiting to do the IO and another logical thread will start running. Because in a lot of cases in network programming, it's really the IO that really matters. So long as you can, if you've got to go out and, go to 5 different web services and get results from them and then compute your result from that, what's important is you don't do one, wait for that, and do the other and wait for that. You want to be waiting at the same time. Whether you're actually using multiple cores is not such a big deal. It's more about having the IO work in parallel.
And then to sort of bring this back to the visual aspects, the concurrent operations in a function can be defined by multiple named workers. Can you describe that and how that works for us?
Right. So within a function, and this is going back to the sequence diagram model, at the top level within a function, you can have blocks that are named workers, and those blocks run in parallel, and they can exchange messages with each other. And the messages are matched up at compile time to make sure that everyone, so if you think of a sequence diagram, your arrows match up. So the arrows in the sequence diagram, there'll be a send in one block and a receive from the other block. And in order to be able to build that sequence diagram, you'll check that the sends and the receives in each block match up. It's probably easier with a picture. You can't draw, a sequence diagram, you have a sender and receiver. And if one block is sending and one block is receiving, in order to be able to draw a diagram with an arrow from one to the other, you've got to have a send in one and receive in the other, or vice versa. So that is part of the semantics of the language, that you can match those lines up. And what the static checking does is check that your sends and receives to match up, and so you can actually get every line as a sender and receiver, which is a somewhat restrictive model, but when it applies to your problem, you detect a lot of problems at compile time that would not otherwise be detectable. And you also get the diagram that actually gives you real insight into what your program is doing in terms of network interaction.
What's next for Ballerina? What are you currently working on?
Currently, we are working on getting the Java version. We're just in the process of finishing up the beta for the kind of major release we have as well, that we call it Swan Lake, which is the kind of the first.
Oh, I'm loving this.
The next one's going to be Nutcracker.
Excellent. So you're working your way through all the Tchaikovsky ballets. You need a Sleeping Beauty and a Romeo and Juliet, I think.
Anyway, so we're starting with Swan Lake, and the idea is going to be that really represents the language being mature, not language being perfect. There's tons of stuff we can do, but we've got a fairly comprehensive set of language features, which we're happy with. There's plenty of stuff we want to do, but it's a solid base. And we'll have a Java-based implementation that, is a solid implementation of those features. And so we're just finishing that up. I guess several things are going in parallel, but I think that the next thing is, which is what I'm working on, is doing a native implementation. So targeting LLVM, being able to use native executables that don't have any dependency on Java. And we're also, which is interesting, doing it in Ballerina. So we're trying to write a Ballerina compiler in Ballerina. This is not what Ballerina is designed for. Obviously, Ballerina is designed for writing relatively small programs to enterprise integration. So using it to write a compiler is pushing it to its limits. But I think that that's good because it pushes the current implementation and it pushes the language. And I think one of the goals of Ballerina is that you shouldn't run into a wall. You should be able to start small, and as your program grows, Ballerina will grow with you. And I think if we can write a compiler in Ballerina, then I think whatever enterprise integration problem you need to solve, you can be confident that Ballerina will have sufficient horsepower to be able to do it.
If listeners want to find out more about the language and maybe have a play with it, see what they think, where's the best place for them to get started?
The ballerina.io website.
Nice, easy answer.
Nice, easy answer. I think everything's linked to from there.
Excellent. All right, I shall include a link to that in the show notes. And with that, James, thank you very much indeed for joining me today on the InfoQ podcast.
Thank you for having me. I enjoyed our conversation.